Hello, and welcome to the latest seminar in the Smart Mobility Connection series. My name is Lisa K. Schweier, and I am the Program Manager for the Traffic 21 Institute and the Mobility 21 University Transportation Center. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 UTC as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and to foster future interdisciplinary collaboration. Please note this session is being recorded and all participants' microphones are muted. To ask a question, send a message through the chat box to the speaker or to Joy and I, and we will make sure they get asked. You do not need to wait until the end of the presentation to send your questions. So now I would like to introduce today's speakers. Srinivasa Narasimhan is the Interim Director and Professor of the Robotics Institute at Carnegie Mellon University. His group focuses on novel techniques for imaging, illumination, and light transport to enable applications in vision, graphics, robotics, agriculture, and medical imaging. His works have received numerous awards, have been covered in popular press, and is highlighted by NSF and NAE. He is the co-inventor of programmable headlights, Aqualux, 3D display, assorted pixels, motion-aware cameras, Episan 360, Episan 3D, Epi2 F3D, and programmable triangulation light curtains. He has co-chaired several conferences and serves as area chair of top computer vision conferences. And joining him today is Robert Tamburo, who's a senior project scientist at Carnegie Mellon University in the Robotics Institute. He obtained his PhD in bioengineering at the University of Pittsburgh. He was a research fellow at Intel Labs, where he developed algorithms to detect features indicative of diabetic retinopathy. His current area of research is the development of imaging and illumination systems. His work has been presented at top biomedical imaging and computer vision conferences. He's received a Best Paper Honorable Mention Award at IEEE 2012 and has been covered in the media. He is co-inventor and lead developer of programmable headlights. Please help me welcome Srinivas and Robert as they tell us about their University Transportation Center project, Visual Understanding of Traffic at Intersections.
Hey, thank you, Lisa K, and thanks for the kind introduction. Again, as Lisa K mentioned, I'm Srinivasa Narasimhan. I'm the Interim Director at the Robotics Institute. And this project that we're going to talk about has been in the works for multiple years, related to computer vision technologies for smart cities and intelligent transportation. So we thank Traffic 21 and Mobility 21 for all the support. So really this most of this talk is going to be given by Robert Tamburo, who's the real leader in all of this stuff. And what I want to say at the outset is that we see this project as an opportunity to collaborate with the broader Traffic 21 and Mobility 21 communities. We are really computer vision people. We want to develop state-of-the-art computer vision technologies, but we look to the broader community in CMU and elsewhere to tell us how to make this useful for Traffic 21 and Mobility 21. So with that, so this is really a call for collaboration. If you guys wanted data from all of the stuff that we're going to talk about today, please feel free to reach out. If you want us to run certain analytics, we can do that. Feel free to reach out. We can also give you our analytics so that you can do more high-level analysis as well. So, so we hope that after this lecture, we will have much more collaboration. So with that, let me turn it over to Robert. And as Lisa K mentioned, Please type in your questions and we will jump in and answer as and when we see them. Thank you. So Robert, why don't you share the screen?
Good afternoon. Thanks for the introduction, Srinivas. One second, I'm getting all these messages. Okay, so as Srinivas mentioned, today we're discussing how visual data and computer vision can be used to better understand the dynamics of traffic intersections. So I'm going to start the talk off by, explaining why we're interested in intersections. So intersections are our primary interest because they are inherently a dangerous component of the roadway system. That's because they are planned points of conflict between vehicles and other vehicles and people. And at intersections, there occurs a disproportionate number of crashes as well as fatal crashes. So if you think of crashes and the causes of crashes, most of them occur because of driver error. But as you will see in the next few slides, that the design of intersections also plays a part in that. So in this first example, we're showing the most dangerous intersection in Allegheny, which is kind of interesting because Allegheny County has the most number of crashes in all of PA. So that was a little surprising to me. But at the West End Bridge, if you've ever crossed it, you know that it's a very chaotic and confusing intersection, and that happens to be the worst performing intersection in all of Allegheny County. So if you look at the picture on the left, you can see that there's a large number of roads that are kind of meeting it very closely at different areas, and that creates a lot of problems for drivers, especially if you're not used to the Pittsburgh left, then you know that could be very confusing to people. On the right is an intersection near CMU's campus at 5th Avenue and Morewood Avenue. At this intersection is laid out very interestingly because the Morewood Avenue, which is going up and down in the image, staggers across the intersection. So vehicles have to actually kind of swerve to stay in their lane as they pass through the intersection. So just to kind of give you a preview of what we're presenting, what you're seeing in this image is our algorithms that can kind of compute the trajectory of vehicles that pass through the intersection. So these colored lines are the path that vehicles take through the intersection. And below that is a speed profile. So we're able to compute the speed of vehicles from a single camera as they pass through the intersection. So in combination, the trajectory and the profiles give us an indication of the behavior of vehicles as they pass through the intersection. What's interesting in this graphic is that if you focus on the green lines, you can see that cars, as they pass through the intersection, not only do they swerve, as you can see, the trajectory kind of bends towards the bottom of the intersection, but the speed decelerates through the intersection, and then as they pass the intersection, they start to accelerate. So these are a type of questions that we're interested in, the analytics that we're interested in. So instead of just simple analytics like counting vehicles, we want to know like what the behavior of vehicles are. So in this next example are just some other problematic intersections in the United States. So these are intersections where a lot of accidents occur, and we know accidents occur because when there's an accident, the police are called and they file a report. Every state submits their reports to a national database, and we could see where these accidents occur. So again, we're interested in developing algorithms, specifically, vision-based algorithms that can give us more information about what's happening, what's leading to these accidents, so that we have a better understanding of what's happening, and hopefully that we could provide information that will make these intersections safer. So we don't have too many roundabouts in the United States, but it's an interesting type of intersection because there's a lot of different traffic flows happening. So in Michigan, there's like a very problematic one where a lot of accidents occur. But what I found fascinating was this roundabout in Swindon, England, commonly referred to as a magic roundabout. If If you look at YouTube videos of this, of cars traveling, it's really hypnotizing because there's like 7 different circles in this roundabout and traffic flows in 2 different directions. So I don't have the crash statistics of this roundabout, but just from a research perspective and understanding the activity in this roundabout, it would be very interesting to see how traffic flows in this roundabout. And as you can see in the picture, there's a lot of people on the periphery of the roundabout. It's unclear if they're just watching the cars go by or if they're trying to cross. But developing computer algorithms that can tell us like high-level analytics of the behavior of these people in these vehicles can ultimately lead to a safer type of intersection. So if you're familiar with the Pittsburgh area, there's the Parkway East is notorious for being problematic for merging onto the highway. So there's surprisingly there's even worse interchanges in the United States. In Kansas City, there's the Alphabet Loop, which has 23 exits over 4 miles. So it's very chaotic. If you think of interchange, it's basically it's an intersection where you're trying to merge with vehicles that are traveling at high speed. So it's very dangerous. If you ever try to merge on the Parkway East, you've probably seen a fender bender at one of the merge points. And that's been I think for the past few years, it's been a point of interest in trying to improve these interchanges for less collisions. So this video is from Vietnam. I found it's kind of very interesting to watch, fascinating. So this intersection is in Vietnam. It's very wide. There are no traffic signals. There are no stop signs. There are no marked lanes. But as you can see, like the people are, they're kind of collaborating or communicating in some way. Maybe they're just used to this type of chaos, but they're able to navigate this intersection without colliding. But again, so our interest is in developing algorithms to understand the activity that's happening in intersections like this. So if we could put an intersection here, we would we'd have a clear understanding of how people are able to navigate such a poorly, well, I shouldn't say poorly, but chaotic intersection. So those are some, that's kind of the motivation for the why we're interested in intersections. So we're not only interested in how many vehicles pass through the intersection or how many people walk across the intersection, but there are many other activities that we have in mind or that we're interested in, and trying to answer these questions is kind of the goal through developing specialized algorithms based on visual data. So shown in orange are activities or analytics that can be answered. These questions can be answered with very simple or off-the-shelf almost computer vision algorithms. So that includes questions like, can we count how many vehicles, pedestrians, cyclists cross the intersection, and what time they cross the intersection. So in Pittsburgh, there's this push to add bike lanes throughout the city. So the question is, if you're a biker, you might want to know when the bike lane is used most frequently. So if you're like training for a triathlon, you might want to go during a less frequently used period. So something I've noticed with the bike lanes is that people tend to block the bike lanes quite often. And I think this information might be useful for the city as well as in terms of enforcement, as well as people riding their bikes. So parking in Pittsburgh is at quite a premium. So it would be useful to know how often cars are parked on the street, what type of cars are parked on the street. Maybe there's this in other areas. There's these systems where the payment for parking kind of flexes based on usage. So we can have like a real-time system that can adaptively adjust the rate of parking based on who's parking there. And we could do, we're interested in learning more about how the buses operate, specifically how people get on and off, how many people get on and off the bus. And if we can, accurately detect people at the bus stop and track them, we could determine, how many people are waiting and how long it takes for them to enter a bus. So this is information we think that could be useful to Port Authority. So what I'm going to present is less of those kind of simple analytics and more of the advanced analytics that require more sophisticated computer vision algorithms, and these are shown as blue text. So as we went through those intersection slides, I talked a lot about crashes. That's known data. What's not reported is how many near crashes there are and other anomalies, like how many people swerve or how many people make a turn when they're not supposed to, or make a U-turn. So these are the type of high-level analytics that we're interested in. We want to be able to determine whether vehicles swerve in their lane. Maybe some drivers are behaving erratically. So there's a lot of distracted driving these days. So we think we can answer these questions with the algorithms that we're working on. And then since the cameras are, as I'll talk about this, but most of the cameras that we're planning to use are fixed on the infrastructure. So they're kind of in static locations where they are not only observing the intersection and the people and the vehicles in the intersection, we can look at the infrastructure itself and determine, whether the infrastructure is damaged. So is there a pothole in the road? Is the curb crumbling? So we could, assess whether that's happening and the extent of the damage and the location of the damage, information that could be used for, the city. And then, we have worked a little bit with, determining whether the road conditions are suitable for driving. So whether it's like a heavy downpour, if they're covered in snow, and if they're covered in snow, has a snowplow been through the area or not? So these are kind of, a lot of this information is very high level. It's more than just counting things. It's understanding behavior and more advanced information that can be useful for like intelligent transportation systems.
Hey, Robert, just to jump in, there's a question about examining applications for persons with disabilities. I think what Robert is presenting here is sort of a partial list of questions. It's by no means a complete set. And if somebody had to identify disabled people as they are moving about in the intersection, or issues when they are crossing the intersection, these things we can identify, and that's something that we are continuing to work on. And if you're interested in that, please contact us and we'll try to develop a vision algorithm for that. Robert, go ahead.
Okay. So in addition to different types of activities, we look at different scales of activities. These are activities that occur in different sizes of areas. So we consider small activities to be confined to small areas like libraries and parks. So what you're seeing, I should back up, is a rough diagram of the area around CMU. So you kind of see like the coffee shops and the college buildings. So small activities are confined to smaller areas, so the activity is constrained by this smaller space, and those are indicated by the orange arrows. And what you see in the upper right corner is, some people having a snowball fight in the park, and we're able to reconstruct their 3D paths and track them with multiple cameras. The majority of this talk is going to focus on medium activity, such as intersections, as I talked about. These algorithms are fairly advanced. We can do 3D, 4D reconstruction, so we can recreate the paths of vehicles as they pass through the intersection, as well as their speed and trajectory. And in the future, maybe, we might be able to do like predictive behavior of people and vehicles as well. And the next scale would be a much larger size, where we want to understand the activity in the entire neighborhood. So obviously you can't have like a single camera that captures, the activity in the entire neighborhood. So we need a network of cameras and computers that can communicate with each other and relay information. So just to put that in context, to give an example, so we create these activity maps for this entire region because the systems are collaborating, they're sharing information. Average or common activity might be, every weekday at noon, people leave college buildings and they run to the cafeteria or the restaurant to get lunch. So you're going to see a spike in activity in those areas. So that's kind of, the normal activity. And we're also interested in abnormal activity or anomalies. So, if you create an activity map today, when, these restaurants are, mostly shut down, there's going to be a big difference in activity. And you can extend this, if you collect these activity maps over time and you get an understanding of what quote unquote normal activity is, you can find these anomalies. And so, for example, say there's like a protest or something at an intersection, and the system there, the node there, or the platform there notices this abnormal activity. There's a lot of activity here that's just, I don't know what's going on. So I can relay that information to other nodes in the system, and just imagine maybe these systems are connected to the traffic lights. So, they're telling these nodes that there's all this activity coming your way. Maybe you can, adjust the timing of the traffic lights to optimize traffic flow. So we're interested in many types of activities and different scales of activities. So right now we're interested in, we're focused on, our work has been focused on medium scale activities, intersections. And we have a platform that we have developed called Platform PITTSBURGH, where we have cameras, computing algorithm at the edge or at the intersection itself. And the goal is to kind of create a template or a prototype for how we would scale that up to cover, large scale activity. So specifically, we want to understand human activity, calculate low level and high level analytics with a emphasis on high level analytics. And another component is that we want to be able to do these analyses, processing the data and coming up with these analytics in real time. And the goal of the main objective of that is that we're shifting to a world where vehicles are driving themselves, robots are going to be navigating the roads, and we think that this type of real-time information can be useful for these autonomous vehicles for their own path planning. So our work requires a lot of data, a lot of data. So we kind of develop the algorithms on 3 different types of data sources. One is handheld cameras. So in developing the algorithms, we collected a lot of data from 10 different intersections around Pittsburgh using smartphones and GoPros. And here's an example of some of the video that we've captured. And again, these data are collected to develop these algorithms, which are based on deep learning models. So we develop these algorithms on this data, and we refine it over time as we continuously collect data. And as Srinivasa mentioned, we have all this data, and we're willing to share it with anyone that wants to collaborate. The second source of data are what we refer to as infrastructure cameras. We've had 4 deployments around the city of Pittsburgh, more specifically around the campus, CMU's campus. So our very first kind of pilot was in front of Noel Simon Hall. We had a cabinet mounted on a light pole with some computers in it with a couple of cameras. So that allowed us to not only develop algorithms, but also determine kind of the compute needs for the type of algorithms that we wanted. The second deployment was in the CIC building, where we are interested in assessing air quality through video. And then the 2 most recent deployment locations are on the roof of the III building and at the intersection of 5th Ave and Craig Street. So on the III building, we have 3 total cameras. 2 are directed towards the Craig Street intersection, and they are configured in a stereo configuration so we can do 3D estimations. The 5th Ave and Craig Street intersection was kind of our big test, if you will, where we installed a bunch of cameras on the traffic signal poles, and we had a cabinet mounted on a utility pole with all of our computer equipment. And that was all made possible through City of Pittsburgh, DOMI, and Metro 21. And we have 2 future deployments that we are currently exploring. One is in the Morewood Gardens parking lot, where we're going to, kind of develop algorithms to deliver analytics to the parking department that they find interesting, such as, capacity, like how many cars are actually parked, how many spaces are available, what kind of, how long does it take a person to find a parking spot, what kind of, what lanes do they drive around to find a parking spot, stuff like that. And then our next intersection deployment is going to be focused at the 5th Ave and Morewood intersection, which is in front of the cut on CMU. And we're going to have, hopefully, cameras and computers mounted on Wagner Hall, which gives us a nice view of the intersection as well as a majority of Forbes Avenue. So the 5th Ave and Craig Street deployment, this is just to give an idea of what type of equipment we have at that intersection. And again, the goal is to do computer vision in real time, specifically, calculating these analytics in real time and eventually transmitting, sparse information to connected vehicles. So we have 8 cameras at this intersection mounted on traffic poles. We have 4 computers in a cabinet at the intersection to ingest the data as well as perform the analysis. We have tons of storage for saving the data, and we have capabilities for remote control of the system. So, if a computer crashes, we can reboot it remotely instead of, climbing up the pole and hard resetting the computer. And access to the computer, we use Comcast 535 internet plan. So here's an example of the type of video that we can acquire at the 2 infrastructure deployment locations. On the left are cameras from the 5th Ave and Craig Street intersection. And on the right are the III cameras. And as you can see, the III cameras are very similar because, they're basically right next to each other. But again, we can use that configuration to do 3D reconstruction and estimate depth and vehicles and people.
Hey, Robert, there are a couple of questions about the quality of the cameras. Can you say a little bit about the resolution, dynamics,
sure.
all of these things, right?
So, so specifically for the 2 deployments that we have currently, so the III building, we have machine vision cameras. So they are very high quality cameras. They output the data in raw format. So you can find a lot of minute details in the image. At the 5th Ave and Craig Street intersection, we use, I can go back. It's this Panasonic camera. It's a high resolution security camera, 4K resolution. It has near infrared imaging as well as light sources internally. So when it gets dark, you can still see things at night. So those are for our deployments. As I mentioned, initial some other work is done with data that is captured with handheld cameras. So we use smartphones like iPhones and Samsung Galaxies, and as well as GoPros. And the final source of data that we use to develop our algorithms are online sources. So there's quite a few live video feeds in different towns. We use one from Jackson, Wyoming, and you'll see results of those in a bit. Other online sources are, a lot of conferences have these kind of challenges. So there's specifically a data set that we use called AI City. So again, there's a lot of different online sources for data. And as you'll see in the next slide, we have a kind of a basic processing platform that is based on deep learning. So we need a lot of data to train our models. The pipeline itself can do detection, tracking, and 3D, 4D reconstruction. So again, we use deep learning, so we need a lot of data for training. We've partnered with Sensors. They provide an interface where we can feed them our data, and the data is given to people who manually label the data. We're mostly concerned right now with how many vehicles are in the scene, but we can ask any type of question. and people will manually label the data. So we've had them manually label key points on vehicles. They've labeled video with people and vehicles in video. So this has made our life very easy, or easier, for training models to detect vehicles and people. So, oops. So this is like, so this is an example of what our pipeline can do for detecting and tracking vehicles. So this is a camera at the intersection of 5th and Craig. So what you're seeing are the boxes around vehicles are successfully detected vehicles. Each color is unique to the vehicle, so you could tell that if the color doesn't change, it means we're successfully tracking it through all of the frames as the vehicles pass through the intersection. So detecting vehicles, there's a lot of like off-the-shelf stuff you can use, but we paid particular attention to being able to detect and track vehicles in the presence of occlusion. So you can see as cars pass each other and obstruct each other, we're still able to detect them. So as this on the left, you can see a camper pulling up and it's blocking this black car, but we can still detect the black car. Oops. So this is an example of applying our pipeline to online data. So Jackson, Wyoming has a YouTube feed of many cameras. So on the left is a camera in town square. On the right is another camera kind of in the center part of this little community. And what we're doing here is, we're not just detecting and tracking vehicles. We're able to estimate the key points of the vehicle. These are, we can tell. So based on the key points, we can tell what side of the vehicle we're looking at, what kind of, is the vehicle turning left or right. So these key points allow us to determine the orientation of the vehicle and understand better, more accurately, what the vehicle is actually doing as it's driving. So as you can see in the right video, there's a lot of light poles that and trees that the vehicles pass by. There's some miscalculations, but overall, it performs better than anything out there in terms of detecting the vehicles and estimating the key points. Okay, so I've talked about detecting vehicles, tracking vehicles, and estimating their key points. Another thing that we are doing is performing 3D reconstruction. So we can actually see where the vehicle is in the intersection in 3D space. So what you're seeing in this first video that's playing is Butler Street and 40th Street. You can see the outline of the vehicle and kind of a trail of where it's been. So it's kind of a instantaneous trajectory of the vehicle. So you can observe the pattern. And over time, you can accumulate these trajectories or these paths and get an idea of where all the vehicles have traveled, how the vehicles have traveled to the intersection. So we've done this for many intersections around the city. These are just 4 of them, which I'll play. Okay, so when we do this, we perform the 3D reconstruction, and then we can reproject it onto the map. So as the videos play, you can see kind of the arrangement of the intersection and the surrounding area. Okay, so back to this diagram. So, there's a kind of a difference between real-time and near real-time analytics. Shown in blue, we think, 3D information can be very useful for autonomous vehicles as well as autonomous robots if we can transmit that information wirelessly, for example, with 5G. Because we're not transferring like full images, we're just transferring, say trajectories or, position of vehicles or the speed of vehicles. It doesn't take too long to send that data, so we're not bandwidth limited. So we built off of our initial platform where we can do 3D reconstruction, and now we can do 4D reconstruction. So this is the intersection of 5th Avenue and Morewood. And so what you're seeing here is instead of just calculating the trajectories of individual vehicles, we've kind of made an assumption on an observation that most vehicles that pass through an intersection kind of follow the same path. So we can cluster individual trajectories over time and get an idea of what the kind of common path that most vehicles travel. And if there is a vehicle that passes through the intersection that doesn't, that the trajectory is not near the kind of average trajectory, we take that as an anomalous event. So again, we're interested in anomalies because those are not often captured in any sort of reports. So what you're saying here is, all these colors correspond to different clustered trajectories. This orange one is the one that I showed earlier where the vehicle's crossing through this staggered street. So as this video plays, you can see the trajectories in this 3D space. And again, we're doing this through time, which makes it 4D. So at any given time, we can tell where a vehicle is and where it's going. So that video is from Jackson, Wyoming. This one, where'd it go? Jackson, Wyoming. So we built off of that to really get a better understanding of high-level traffic understanding, where we can not only know the trajectory and the position of vehicles, but we can also know the speed of the vehicles. So what we're seeing here on the left is a video which will show the 4D reconstruction, specifically vehicles as they pass through the intersection and the trajectory that they follow. And the orange dashed line is the field of view of the camera. So as vehicles kind of approach that, they're going to disappear because they're no longer captured by the camera. In the upper right, after we do the 4D reconstruction, we project those results onto the video. That allows us to kind of qualitatively assess whether or not our reconstruction is accurate. So, if we see like the outline of a car in the middle of the sky, we know it's not accurate. And then another thing we can do is, we're doing 3D reconstruction. We can look at the speed profile of vehicles as they pass through the intersection. So that's a plot of speed versus time. So as vehicles move, you can get an idea of how fast they are moving. And again, to reiterate, the idea here is to get an idea of what the common behavior of drivers through the intersection are. And by default, if there is any sort of anomaly to that standard, we know that there's something else going on. So it might be an accident, it might be a near accident, it could be someone making a wrong turn. So as this video plays, you will see vehicles passing through the intersection, and you can see all the colors are constant through all the videos. So a red trajectory corresponds to the speed profile. So again, the speed profile, so that tells us, it's speed versus time. So we get an idea of, whether a car is slowing down or speeding up. If they are abruptly slowing down, that's an indication that there might have been an anomalous event, and we might want to look at that to understand what's happening. So this is the data set from the AI City Challenge. This next data set where we show results is this Forbes and Morewood, or 5th and Morewood intersection. So as cars pass through, you kind of see, if you pay attention to some of the trajectories, you can see how the vehicles have to kind of swerve to stay in the lane. Specifically, I'm talking about Morewood Avenue. Again, so these are all, I don't know if I mentioned it, but these are this analysis, these algorithms are used. So we're doing 3D reconstruction with single cameras. So usually you need 2 cameras to do stereo or 3D reconstruction. So we're able to do it with a single camera. Okay, so let me start that over. So what we showed in the previous videos were kind of, just normal behavior of vehicles. They're just kind of going about their business. There's no sort of anomalous events happening. So with the Jackson Hole video feed, we were able to detect anomalies in the behavior of these vehicles. So in this first video, so I'm going to show like 3 or 4 videos in a row. So this first slide shows an anomalous event that we detected. So we didn't know what it was. We just knew something happened. So we looked at the speed profile and we noticed that, you know, this vehicle with the green trajectory was kind of decelerating pretty quickly. As you can see from the video in the upper right, it's the green vehicle is trying to make a left while a vehicle's coming towards them. So they both stopped very quickly. Our system saw that the speed profile was not normal. So it kind of flagged it, and we looked at the video, and then we saw that the vehicle was trying to make a left-hand turn, maybe when they weren't supposed to. So in this next video, so again, our algorithm doesn't say whether there's a collision or a near miss. It just says, you know, there's something weird with the trajectory. You know, this vehicle traveled a path that is not normal, or the vehicle had a speed profile that is not normal. So it just so happens in this video, you know, the sequence was flagged because the speed profile was a little abnormal. So in this video, there's an actual collision. So I want to warn you, the video in the upper right actually shows like a vehicle hitting a person riding the bicycle. Fortunately, the person riding the bicycle was not injured. There were no injuries at all. So I just want to warn you before I start the video. So what you see is, you know, the person gets hit, but if you look at the speed profile of the red vehicle, and it's going to loop, you can see there's kind of a drastic decrease in the speed of the vehicle, and that was enough of a difference from the normal for us to flag this video. So again, we flagged this video. We didn't know what happened. We saw that the speed profile was abnormal. We looked at the video, and lo and behold, there's a collision. In this next video, so again, I just want to reiterate, we don't actually know what we're detecting. We just know that there's something wrong in terms of the trajectory of the vehicles or the speed. So this video was flagged because a vehicle was turning when they weren't supposed to. They were making a left-hand turn. So we didn't know what was happening. We had to go to Google Maps and, you know, look at the street view, and we noticed, hey, you know, this person made a left-hand turn when they weren't supposed to. So that's the vehicle with the red kind of trails behind it. So similar to the 3D reconstruction information that we're able to deliver, we think that we can do, you know, we could deliver this information, which would be, you know, this is much more rich kind of information. It tells you, you know, 3D position, it tells you speed. If we could deliver this to autonomous vehicles, they can use this for their decision making. So in the midst of this COVID-19 outbreak, we thought we could, you know, really make use of our low level analytics. So we looked at the activity of people and vehicles. This is in Jackson, Wyoming, this video stream. So what you're seeing here in the orange lines show either person or car activity. And that's plotted against the number of COVID cases. And the big dips in the curve correspond to the weekends. So that's not abnormal, but you can see that around March 19th, when the governor of Wyoming started closing down public spaces, the activity dropped as expected. And then we looked at a parking lot near CMU. This is I think it's the museum parking lot. So we compared last year's data versus this year's data from March to the end of April. So last year's data is shown in orange. This year's data is shown in purple. And then you can see the purple line dips quite dramatically around March 22nd when the governor issued non-essential businesses to close. So all expected, but you know, these are interesting trends that we can look at with low-level analytics. So we took it a step further, and we thought, the governor issued, closing of non-essential businesses. You're supposed to practice, social distancing. So we thought, can we use these the cameras on top of the III roof to determine whether social distancing is being practiced. So we're able to, with these cameras, we estimate the ground plane, and we can estimate the distance to each detected vehicle person, and then we can calculate the distance between people to better understand if social distancing is being practiced. So on the left, you can see that most people actually everybody is adhering to the social distancing guidelines. They're shown in green, so they're at least 6 feet apart. On the right, there's not quite enough social distancing being practiced, but this is something that could be useful to people, and I'll talk about that in a bit. So the other issue is, are people wearing masks? So we have a simple detector that can vary, it's based on deep learning, that can determine whether a person's wearing a mask or not. So these are preliminary results, and we're training models to perform more robustly. But as you can see in these two images, we can, very accurately determine whether or not a person's wearing a mask or not. So going back to our platform, this is kind of a, not necessarily a real-time application, with these behavioral analytics. So, so if you imagine, so we're thinking, you can use this information to develop a website or an app where someone can log in and say, say you want to go to Starbucks someday and you want to know if people are practicing social distancing or wearing masks near the Starbucks. You log into the app, and then you see that, okay, 10% of people wearing masks, so you decide to stay home that day. So we think this pipeline or this platform can be useful for informing people's decisions during this crisis, this COVID-19 crisis. Okay, so should we stop and take some questions? I see like things flashing on my screen.
I think it's
okay.
So just go ahead, finish it
okay.
up in a few minutes.
Okay, so here we've kind of switched gears a little bit. So up until now, we've talked about calculating analytics based on data from fixed cameras. So we wanted to look at what could we do with moving cameras. So a common thing that's done in computer vision is that you want to know what the depth or the distance to detected objects are. So most computer vision algorithms kind of falter on certain materials. These are materials like bright light sources, or specular objects like mirrors, or shiny reflective surfaces. So the problem with that is that you get incorrect distance. So most autonomous vehicles use some sort of sensor to detect objects around them and know how close they are. So we worked on algorithms that would give us more accurate depth measurements for specific materials. So in this video on the left, so what we do is, instead of having 2 RGB cameras in a stereoscopic setup, we replace one of the RGB cameras with a near infrared camera, because the near infrared camera shows information a little bit differently. So through learning and prediction, we're able to more accurately estimate the distance or the depth to objects of these difficult materials. So what you're seeing here is in the top right is kind of not using our method, which has material awareness. So the depth is all over the place. So for those not familiar with depth maps, it's a this color map. In this color map, red is closer to the vehicle, or our vehicle, or our camera. Blue is further away. So obviously this vehicle should be approximately the same distance away from the vehicle in the top right. So when we incorporate our method, and I'll just play that again, incorporate our method or apply our method to this sequence of videos, you can see that the depth map of this vehicle is more constant, as it should be. In this video, we show how our method can compensate for bright light sources. So if you focus on the taillights, they should be about, the same gradation of blue. They are approximately the same distance away from the car. Whereas in the top right video, you can see there's some minor differences. So the idea here is that, if you can combine, analytics with depth measurements on moving vehicles, then, that's a very rich data set that you can use to navigate your vehicle. So what we did here was we combined this method of estimating depth to detected vehicles, and we applied a kind of vehicle detector. And what we're showing in the left top video are vehicles that are closest to our system, and they're highlighted in red boxes. The lower left is a disparity map, which is inversely related to distance. In the upper right, we can estimate the speed because we're doing 3D stuff. We can estimate the speed of our vehicle, and then we can show, calculate the distance to the closest vehicle. And in the lower right shows the movement of our vehicle throughout Pittsburgh. So we don't move too much, but you'll see that as the video plays, that as vehicles that are closer to the vehicle, our vehicle are highlighted in red. And again, we can estimate distance to these vehicles. So again, any autonomous system is going to need information like this to avoid collisions and just to have a better understanding of their environment. So if you can imagine a system where we take all of the analytics that I discussed previously, the estimation of trajectories and the behavioral patterns of vehicles, and we can extend this to vehicles and put this on moving vehicles, then we have a very clear understanding of the scene as we're moving, not just in static locations at intersections, but as we're moving. So we can detect the presence of not just that a car is close to us, but that a car is swerving towards us, or a car is it is rapidly accelerating, deaccelerating. Maybe there's an aggressive driver. So it's a much more rich understanding of the environment around the vehicle. So this shows just a different location, very similar thing. So you can see, as vehicles approach our vehicle, they're highlighted in red because they're closest. So this is around CMU's campus. I forget what the street's called, but it's between the Heinz Chapel. I think it's Dithridge, but okay, so since we're capturing a lot of video, not only to calculate these analytics, but also to train our models, the issue of maintaining privacy always comes up. So we have methods to automatically detect license plates and faces, and then to blur them so that they're not identifiable. So we do this for any data set that we release publicly, and to ensure maximum privacy, we only store data for short periods of time, usually just to train our models, and those data are stored on secure models or secure servers. And just one other thing. So I should have mentioned this earlier. So when I say tracking, I don't mean that we're actually tracking an individual through time. We don't assign a specific label. So we know that, Bob is always passing through this intersection at 3 p.m. It just means that through a sequence of frames, once we detect a person, we can consistently detect a person throughout the rest of the frames within the field of view of the camera. So we never identify people, we never identify cars. We don't know Jim from Bob. So, we want to make sure that, everybody's privacy is protected.
Hey, Robert, you have 1 minute.
Okay, almost done. So as Srinivasa mentioned, we've collected a lot of data, and we are happy to share it for anyone out there doing any sort of research that would benefit from it. We have data set, a already published data set from 18 cameras around Pittsburgh at different intersections. Along with the actual images and videos, you get vehicles that are labeled, as well as manual annotations of the key points. So this is an ongoing data collection, so it's continuously evolving. We also have images and labels from the infrastructure cameras at 5th Avenue and Craig Street and Triple I Building. We're more than happy to share these with you. You know, as Srinivasa mentioned, we welcome any sort of collaboration. If you have some data, you know, whether it's offline data or you actually have a camera with a live feed, and any of these analytics or algorithms that interest you, we're happy to apply them to your data. And if you have, you know, I had showed that slide with all of the questions on it. If you have some question that wasn't on the list, or maybe some question we haven't addressed yet, and you have a data set, we're more than happy to work with you and develop an algorithm that will answer your questions. So,
Oh, sorry. Go ahead, because
I have 2 slides left.
okay, go ahead.
Hey, Robert, I think we should stop and ask for any questions. So
Okay.
you need to stop at 1.
Yeah, and actually, if you can stop sharing your screen at this point, I'm gonna put back up here. And we actually are out of time, so I'm glad we were able to take some questions and answers throughout the presentation. And Robert, I'd like to thank you and Srinivas for sharing your work today. We had a lot of attendees, over 100 people were logged in, so we'd like to thank everyone for joining us. As I mentioned earlier, today's presentation will be posted on the Mobility 21 website on the What's Happening page, and it will include a link to the video of today's session. This afternoon, you'll be receiving an email asking you to take a short survey about today's SMC. Please take a few minutes to provide your feedback. And for students who are on the call who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation with fellow transportation nerds. Our SMC series will be resuming in the fall semester on September 11th. So as you've signed up for these, you will get invited to that first session coming back in the fall. So please watch your email for that. Again, thanks for attending today, and please feel free to contact me with any additional questions. Thanks, everyone.